Well, thank you. Throughout most of my adult life, I've been engaged with the thought of Kurt Gödel, and I think I'd be an entirely different person if it wasn't for the rich set of insightful ideas that he left us. And I'm sure that most people in this room feel the same way, so you can understand that it's a great honor to receive this award. I'm grateful for the encouragement and support given to the area and the opportunity to continue to engage with the thoughts of that great mind. What I want to do today is talk about two themes from Gödel that are dear to me. The first concerns the nature of reason in mathematics, and I'm going to approach this through the question of absolute undecidability. That's whether there could be questions which are not just relatively undecidable to a given system, but in some sense absolutely undecidable. The second concerns the question of realism in mathematics, and I want to approach that through the question of whether there could be, in some sense, a bifurcation in set theory, in particular concerning the higher infinite. So what I want to do in this talk is give a very broad brushstroke overview of the development of the field, and with the hope of situating and motivating my current project. So I want you to just sort of get the big picture and not focus on particular details. So the story begins with the incompleteness theorems. The second incompleteness theorem. Assume that piano arithmetic is inconsistent, where PA is a shorthand for piano arithmetic. Then piano arithmetic cannot prove a particular pi01 sentence, namely the pi01 sentence expressing the consistency of piano arithmetic. This raises two questions. Are such statements absolutely undecidable? And the scare quotes around that term are necessary. And do such statements signal a bifurcation in our conception of the structure of the natural numbers? And the answer, of course, is no. And Gödel was quick to point this out. He said in an unpublished manuscript of 1931, the year in which the incompleteness theorem was published, the statement is not at all absolutely undecidable. Rather, one can always pass to higher systems in which the sentence in question is decidable. In particular, for example, it turns out that analysis is a system higher in this sense than number theory, and the axiom system of set theory is higher still than analysis. So we begin with the natural numbers, which I'm going to draw in the form of a triangle, indicating that I'm really thinking of the hereditarily finite sets. And instead of piano arithmetic, I'm really thinking of the theory ZF minus infinity, which is bi-interpretable with piano arithmetic. And then Gödel's theorem tells us there's a sentence which can't be proved, namely con PA. But we follow the outline of Gödel's remark, and we iterate the power set and write down the associated axioms, namely the axioms of analysis or second-order piano arithmetic, and we find that we can prove that consistency sentence. But then another consistency sentence appears, namely the one for second-order piano arithmetic, but we just continue, go to third-order piano arithmetic. And we continue until we get to a level that satisfies ZFC. Its consistency arises. We go to the next level, second-order ZFC, catch the consistency sentence, and this situation continues. Now, depending on whether you're an optimist or a pessimist, you're going to have a different take on this. If you're a pessimist, you're going to think that for every level, there's a problem, namely the undecided consistency sentence. If you're an optimist, you're going to think for every problem that arises, there's another level that solves it. The trouble is that when one iterates the power set operation in this fashion, the greater expressive resources that become available give rise to much more serious candidates for absolutely undecidable sentences. So it was mentioned in the last talk that a dream is to construct natural mathematical sentences of first-order arithmetic that are independent and lie at various points in the interpretability hierarchy, perhaps bifurcating into incomparable elements. In the case of set theory, it turns out that that's pretty much the norm. Two classic examples of this are the statement that all Lebesgue measurable sets are projective and the continuum hypothesis. I'm not going to go into the details of those statements, apart from saying that they occurred in natural mathematical practice, and that the first statement concerns second-order arithmetic, or the second infinite level of the universe, while the second concerns the third. Now, these sentences were shown to be independent from ZFC plus, various small large cardinals. If CFC is consistent, then ZFC plus CH is consistent, and hence you can't refute CH. This was shown by Gödel, and Cohen proved the companion result. Similar results hold for projective measure and a broad array of mathematical statements, and set theorists using these techniques and elaborations of them showed that many other statements are independent, so much so that what may have started off as a dream started turning into something of a nightmare. So here's what Gödel did. He started with V, and he carved out an inner model by iterating the definable power set instead of the full power set, and the resulting model satisfies CH. Cohen did something much more subtle. He created what one might think of as an outer model, an extension of the universe by a method known as forcing, and in this talk I'm going to concentrate on set forcing, in which the continuum hypothesis fails. So our questions resurface at this point. Are such statements absolutely undecidable? Do such statements signal a bifurcation in our conception of the universe of sets? The situation is now much more delicate. It won't do to just iterate the power set one more time to capture these sentences. But perhaps if one iterates the power set far enough, then one will. Perhaps if there are very large levels of the universe of sets, then these sentences will become decidable. The statements that assert that there are very large levels of the universe of sets are known as large cardinal axioms or axioms of infinity, and that's going to be the focus of my talk. There are two questions that immediately arise concerning them. First, are they justified? And second, do they do the trick in reducing incompleteness? So I'll talk first about the question of justification. Gödel drew a fundamental distinction between intrinsic and extrinsic justifications of new axioms. When discussing intrinsic justifications, he mentions the existence of inaccessibles, molocardinals, and these are small, large cardinal axioms in a very rich hierarchy. Gödel says that these axioms show clearly not only that the axiom system of set theory as used today is incomplete, but also that it can be supplemented without arbitrariness by new axioms, which only, and this is the phrase I want to stress, unfold the content of the concept of set as explained above, where above he explains the iterative conception that I drew a picture of earlier. And he talks of these axioms having intrinsic necessity relative to the iterative conception of set. On the other side, we have extrinsic justifications. Concerning this, he says, even disregarding the intrinsic necessity of some new axiom, and even in case it has no intrinsic necessity at all, a probable decision about its truth is possible also in another way, namely by inductively studying its success. And in a famous passage, he says, there might exist axioms so abundant in their verifiable consequences, shedding so much light upon a whole field, and yielding such powerful methods for solving problems, that no matter whether they are intrinsically necessary, they would have to be accepted at least in the same sense as any well-established physical theory. So I want to first talk about intrinsic justifications and then turn to extrinsic justifications. So intrinsic justifications are supposed to unfold the content of the concept of set. Now, an idea inherent in the iterative conception of set is that the universe is absolutely infinite and hence cannot be described from below. So the idea is you take a purported description of the universe of sets, and since it's absolutely infinite, what you've described is an initial segment of it. You've described a set. And reflection principles aim to articulate this. So schematically, a reflection principle has the following form. If V satisfies that some property holds of a given object, then there exists an earlier level of the universe that satisfies that the reflected version of that property holds of the reflected version of that object. And here I've left the nature of reflection unspecified, but it'll get specified progressively as we continue. So there's two issues. Are reflection principles intrinsically justified on the basis of the iterative conception of set? And do intrinsic justifications, do reflection principles lead to a significant reduction in incompleteness? Now, concerning the first, I think that there are philosophical problems with justifying certain reflection principles. But I don't want to go into that because I think that the mathematical situation is much clearer. And one can show that even if one can give a philosophical justification of reflection principles of higher order, let's say, then it won't be of much help because they're either weak or inconsistent and hence don't lead to a significant reduction in incompleteness. So here's the situation. If you take ZFC and pull away infinity and replacement, and then you add in first-order reflection, where you consider first-order formulas, a parameter is a set and it reflects to itself, then you can reprove infinity and replacement, which are the main axioms of extent in ZFC. And then if you go to second-order formula, higher-order formulas with second-order parameters, then you get inaccessibles, malos, weakly compacts, and indescribables. And to reflect a second-order parameter, the second-order parameter will be a class like A in V. To reflect down to V alpha, you just ask, what would things look like if you were living in V alpha? Well, you would reflect down to A intersect V alpha. So these principles give certain large cardinals. They justify certain large cardinals, assuming that they themselves are justified. They give inaccessibles, malos, weakly compacts, indescribables. The trouble is that as soon as you go to third-order parameters, you get the strongest large cardinal of all, 0 equals 1. So one has to pull back. Now the counterexample that arises motivates a certain restriction on the formulas that's necessary. You have to restrict to what are called positive formulas, and I'm not going to discuss that for reasons of time. But Tate initially isolated this necessary restriction and initiated the study of general reflection principles, and it leads to a hierarchy. The general form is gamma m n, but I'm going to concentrate mainly on the first level, where we have 2 in the superscript, and distinguish between that and all of the remaining levels. So the first theorem is that if there's an Erdős cardinal, kappa omega, then there's a level of the universe which satisfies gamma 2 n reflection for all n. So all the reflection principles on that first layer that I indicated are consistent relative to this large cardinal axiom. Now this large cardinal axiom is quite weak. It's consistent with V equals L, and so it follows immediately that these reflection principles cannot settle our two questions, projective measure or the continuum hypothesis. But Tate showed that those reflection principles are much stronger than what one gets with just second-order parameters. They imply the existence of ineffables. So there's hope that if you go on further to the third layer or the fourth layer, you're going to get significant strength. But it turns out that right at the first layer,